Don't have to scream. Ah.
All right, anything you want to do here? We didn't already cover. 28. This one? All right, 28. Rate of growth of bacteria populations given by y prime equals ky. Hopefully we, a couple things about this one. From a purely review standpoint, hopefully, one of the things we'll want to work on over the course of the next month, I guess, as we're reviewing is just reminding ourselves of all these different things we've talked about. This is that differential equation we memorized. The solution is what? Yeah, some constant C we used, or e to the kt, right? Something like that. So recognizing that would be good. Where y is the number of bacteria present, k is a constant, the initial population is 1,500, and the population quadrupled during the first 2 days. By what factor will the population have increased during the first 3 days? Okay, so there'll be several ways to go about this one. From purely calculus difference and equation standpoint, you could take this equation where y is the number of bacteria, so if the initial population is 1,500, that means you could put 1,500 here, and you could put 0 in over here. Now, we have talked about how the 1,500 could also just go in as a what? Instead of putting it in for the y right there, you could put it where? For the a. That's only true if that initial amount was at times 0, right? Because what's going to happen is e to the 0 here is going to be 1, so a is 1,500. So you could have probably skipped that. But I think that's important to know because sometimes they give you a problem where they don't tell you 1,500 was on day 0. They tell you 1,500 was day 1 or day 2 or something like that. And then that's not your initial amount. That's not the A value. Okay? But you could make that, we talked about that with bank interest. We said, okay, if you got $1,500 on day 10, how much do you have on day 15? You could call day 10 0 and then look for day 5. It'd be the same thing, right? So then you could make the 1,500 be the A, but that would have to be day 0 then. Okay, so that just, it's kind of an important distinction then. Okay, so we could do that. It said it will quadruple during the first 2 days. Well, that means it would be what? Times 4. So it would be 6,000. It would be 6,000 on day 4. Well, so that's like two unknowns, right? So what's that? Oh, it'd be day 2. Yeah, sorry, I was thinking quadruple. So it'd be day 2. And so you'd have that. Okay, so now this is a no calculator one, isn't it? So you would have, divide the 1,500 there, that'd be 4. You'd have e to the 2k. Okay, you can do the log of both sides. Okay, which you get 2k. So k would equal 1/2 ln2, or excuse me, ln4. Although, and so like I said, we're going to talk about another way you could have done this one. But so k equals 1/2 ln4. What's another way to write ln4? And I just want to do this because it's no calculator is going to make this easier. ln4 is like 2 squared, bring the 2 down in front, so that'd be 2 ln2, so those would cancel, and so k is just ln2. Okay, so what do I have now? I have y equals 1,500 e to the ln2 times k, all right? Times t. Okay, times t. All right, so now it says day 3, during the first 3 days. Well, I can now put a 3 in for T. So I've got 1500 E to the, and put a 3 there, so I put it in front, so that's 3 ln2. But what do I notice? What can I do with 3 ln2? I can do the reverse of what I did over here. I can put the 3 up in there, right? 2 cubed is 8, so I get y equals 1500 e to the ln 8. Well, what's e to the ln 8? 8. So this is 1500 times 8. Okay, so now, by what factor will the population have increased? By a factor of 8. Now that was a lot of work that was not all that necessary, just if you understand exponential growth. The fact that it quadrupled in 2 days tells you that this population is doubling. They picked a really easy number. I don't know that they would always do this. So in other words, if there's 1500 at day 0, and then it quadrupled in 2 days, that means it had to have doubled, on day 1, and then it had to double again on day 2, and so what's it got to do on day 3? Double again, right? And so that's going to be 12,000. Well, what factor, what factor is that of what it was before? We'll take 12,000 divided by 1,500 if you get 8. And so you could have done that. And that doesn't happen a whole lot. A lot of times they finagle these problems, so you kind of have to do the calculus they want you to do and not just maybe some other kind of shortcut or whatever. But that's certainly what you could have done there, okay? But again, only because it had quadrupled in 2 days. If they had said it quadrupled in 3 days, then that's different. Then that would not have been a factor of 2, right? But you still could have figured out the factor when it's, because you know it's exponential growth, and that's multiplying by a constant each time. That's what exponential is, okay? But it just depends what that is. It came out nice and even here, and that's what worked out pretty nice, okay? So there'll be a couple different ways to do it. Okay, take another one. All right, what else? Okay. Okay. Rectangles to be inscribed in a semicircle of radius 8. Now there are some assumptions we can make that it's going to be inscribed, it's going to be symmetrical, so it's going to be equal on either side of this center of what the circle would be. So it's a radius of 8. So that doesn't really help you along here, but what it does help you is on this diagonal right here. You know that's going to be 8. Okay? So where it's inscribed, where it's touching the circle is going to look like this. And again, like I said, one side's lying on the diameter of the circle. What's the maximum possible area of the triangle? So if we, it's good review for optimization. So optimization, step 1, identify what you're trying to maximize or minimize. We're trying to find the max area. So we need the area of a rectangle. Okay, well that's length times width. So what we're trying to maximize or minimize, length times width, right? If we call that, that and that. Okay. Step 2 was try to get that, use other information to get that in terms of one variable. So if you want to call that W right here, and what would you know, what would help us, what kind of missing information do we need? to get this other side. The length would be here. So what do we know about this right here? Isn't that got to be half of L, right? Because we know there's going to be symmetry here. So we know this has got to be 1/2 L. So we know that 1/2 L or 1/4 L squared plus W squared would equal 64. Okay, so then we could solve for one of those. It might, to get rid of this fraction, it might be better to solve for the L. So 1/4 L squared equals 64 minus W squared. Now this is a calculator one, right? So now it's got answers like this, but our calculators would actually do that for us, so that's kind of nice. Multiply everything by 4. So what is that, 256 minus 4W squared. And then L would be the square root. We wouldn't have to worry about the negative. Something like that. So we would have A is equal to W times the square root of 256 minus 4W squared. I might be making this, again, I like to do this as review of the calculus kinds of things, but I think that's probably a pretty good way to go. Now, if you get your calculator, what I would do is get my calculator out at this point. I think the intention is to do it, help your calculator, although I don't think it's trying to see if I'm missing something that would make this a little easier. Because some calculators are not going to do the derivative. So that derivative wouldn't be a lot. I mean, it'd be a product rule. It'd be it's not going to be any problem for our calculators. So let's take a look at that. So if you do the derivative and then do a solve and set that equal to 0. Oops. Okay. So I just went on my calculator, did the derivative, did solve, set equal to 0. It came out to be W equals 8 square root 2. That's the answer I got. Okay. However, that's not the answer we want, right? I don't think. They want to know what's the max possible error. Right? So what do we need to do with that? Put it right back into there. Okay, so it'd be 8 square root 2, which I would just do on my calculator, but this would be 256 minus what's 8 square root 2 squared would be 128. That's going to be going to turn out negative inside there. That's not good. What do you get when you put 8 square root 2 in there? Is that negative inside the square root? Or am I just doing that wrong? You got how much? Okay. All right, good. 8 square root 2 squared, wouldn't that be 128? Times 4, wouldn't that be 512? You got 4 square root 2 what, for the area?
No, so when I do it,
Oh, when you did the derivative and solved it? Oh, Yes. I typed mine in wrong. Okay, I typed it in wrong. I didn't type in 4 here when I did my derivative. So, solve, there we go. I was gonna say, 'cause there's no way that can be right. Equals 0. Yeah, 4 square root of 2, there we go. 4 square root of 2, 4 square root of 2. Okay, and then 4 square root of 2 squared would be 32 times 4, 128, square root of 128 times 8 square root of 2. And the final answer comes out what? 64. Okay. So, again, using the calculator to help you with the messy parts. But the key is just getting it set up. Identify what it is you're trying to maximize. Get it in terms of one variable. Use some additional information you have here, which would be this triangle right here. Pythagorean theorem. Get it in terms of one variable. Then, where's a max going to occur? Right? We have endpoints. Remember, what we actually used to go through is endpoints. A lot of times endpoints didn't matter where the derivatives are defined. That kind of stuff. But usually in these problems, not going to be, it's usually pretty straightforward. It's usually, can you get it set up, do the derivatives, set equal to 0, find those issues. Where you're going to run into those endpoint issues with the max, is it like on a free response question, probably in a graphing scenario, and so you have to consider endpoints and stuff like that in those. Okay, what else? One more. Or no more, I don't care. Let's move on. So remember, 2014 packet and this sample 3 we want to be done with next week. So I had said 1 and 4, and I think that left us with like 5 and 6 to do. 2 I said we really can't do. Part of 2 we're going to do today. So you might get out that 2014 packet, because part of number 2 we're going to talk about. Well, if we have time, we'll see how things go. I think we should. We can do one part of number 2, and then the other parts of number 2 we'll leave alone for now. I'll give them back to you after I collect them and look at them. Okay? So just have those handy. Anything else on sample 3? All right. Well, let's go ahead and get your notes out then. And there's a couple things to write down. I wouldn't write down this screen here, but there will be some things that you might want to jot down. So we're gonna go into chapter 7 here. We're gonna go into chapter 7 and talk about the first section, and that is the area between curves. So we're going to revisit this idea of area. So that's why I put this up here. So again, you don't have to write this down. But if we remember what area is now, I didn't put the limit on here, but so I put approximately. But remember, the area, the integral. If we go back to think about integral as area, now we've been talking about integrals a lot of things. Average value, we use integral. We talk about integrals of adder, accumulator. We talked about do the integral of a rate. You get the amount, the net amount of change. So we've talked about integrals a lot of things. But remember, when we first talked about integrals area, and it was area under the curve, and it was possible to have negative area, right? We could have negative area. Now the reason is because what the integral was an adding up of a height and a width. It was adding up of a function value times a width. Now the width was defined to be always positive. The width was always positive. It was this x minus this x, and this x minus this x, and this x minus this x. And we always took the one to the right minus the one to the left. So the one on the right is always bigger than the one on the left. When you subtract, it's going to be positive. So if you remember, we defined delta x to be x sub I plus 1 minus x sub I. Okay, so it was always an x value on the right minus an x value on the left. And so that's why it was always positive. So the width is always going to be positive, but the function height, the function value could be negative. So that's really why area below is negative, right? Now, when we went backwards, the reason that they were opposite is because then your width would be negative, right? Then you're going the other way, then you can argue that the width would be negative, okay? And then that would make everything opposite, okay? But for going this way, the widths are positive, but the function height, like in this one, that would be a negative value. So that's why this would give you a negative number, and that's why that's a negative variable. But if we're going this way, the function heights are positive, right? And so this is positive area. All right. So we want to keep in mind that idea of height times width, Okay, sometimes the heights were positive, sometimes the heights were negative. All right, so now what we want to look at is an area between two curves. So let's look at these two curves right here. So this you could jot down. So let's say we had x squared, and we had cube root of x. Okay, that's what this curve is right here, is cube root of x. Okay, just the x cubed curve, the inverse of the x cubed curve. Okay, and we wanted to do this blue area. Okay, now we've already talked about this. We've already talked about how to get that blue area, we could take the black area, right, which would be the area under the x to the 1/3. So we could take that area, right, and we could subtract the red area, right, which would be the integral from or under x squared dx, right? We said we could just subtract those two areas. So we could take the black area, we could subtract the red area, and that would give us the blue area. And that made sense. And then we said we could put that back into just one integral, which would be x to the 1/3 minus x squared dx. And then whatever this point is, I think this point is 1. I think this is the point 1, 1. Right? 1 squared would be 1, and the cube root of 1 would be 1. So this would be the area from 0 to 1, like that, right? Okay, so now we want to take a little different look at it, though, because not all regions that we have that we're going to do are going to be that nice where we can take one area minus another area. They're not going to be that nice. So we're going to take another look at this blue area, okay? Well, I guess I made it red in this picture. Okay, so we're going to take another look at this red area, and we're going to say, you know what? Let's do the same thing with that area that we did with our other areas. Let's think of it as adding up a bunch of rectangles. Let's put a bunch of rectangles in there. So what I've drawn is a couple of left endpoint rectangles. Does that make sense when you look at it there? That those are left endpoint rectangles. You look at your subdivisions, and we're going to be this wide, and we'll take the left edge of the subinterval, and we'll put two dots, not just a dot on, just not a point on the function, but there's two functions, so we'll put one on each. Okay? Well, doesn't it make sense? Now let's call this function, let's call the x squared function f. Let's call this f of x, and let's call this one g of x. Okay? Now, what would be the height of that first rectangle? And call this point x sub 2, I don't know, whatever. This left end, we'll just call it x sub 2. How would you write the height of that rectangle? In function notation, using g's and f's. What would this height be right here? Wouldn't it be this y value minus that y value? What would be the name of this y value? G of x sub 2. And what would be this y value? F of x sub 2. Right? Now the x sub 2 part don't worry about. But now, why would it be g minus f? Why wouldn't it be f minus g? Because g is the bigger one if we're going to subtract them. So now what this is going to lead us to, and we'll write it down here in a little bit, is that we would determine whether this area was going to be positive or negative in the order we subtract them, wouldn't we? Right? So these are always going to be positive. And we'll see. But when we talk about, so the difference between just doing the area under a curve, that's doing the area from the curve to the x-axis. You can have positive and negative. When we're doing the area between two curves, it's always going to be positive area. Okay? So, and here's another good reason. So the x-axis plays no role here whatsoever. So, because imagine taking these two functions and now just shifting them down a ways. Would that red area change? The red area would still be the same region. If you grab these two functions and moved them both down here, the area between them would still be that red region. It would not change. Now that's different when you have one function, right? You have one function in the x-axis. You move that one function up or down, the area changes because the x-axis doesn't move. You see what I mean? So we're talking about areas between curves, creating a region. Where that region is vertically or horizontally doesn't matter as far as how much area there is. So we're just always going to call it positive area. So it's always going to be the top y value minus the bottom y value to get the curve, to get the height of the rectangle. And then the width, of course, will just be, the width will just be our delta x. And so the integral would be just adding those up. So it would be g of x minus f of x dx. And if you go back to this picture, right, it would just be the top curve, which in this case is x to the 1/3. So the top curve minus the bottom curve, which is x squared. And sure enough, there's our integral right there, right? Without even have to go through these different areas, it's just top curve minus bottom curve, like that. Now what we will do is we'll draw what I call a strip. So what we'll do is we'll just draw a strip in there, which will represent like a rectangle, a really thin one. We'll just think of that being a really thin one. The dx is like the width, right? And we're just adding up all these strips of area. Rectangles, skinny little rectangles, right? Infinite number of them. So we're just going to add up all these rectangles from 0 to 1. So what's the area of these rectangles? The width is the dx. The length of the strip is the height of the rectangles. It's this y value, g of x, x to the 1/3. That's, and you're going to hear me say this a lot. What's the y value of this function? Oh, it's x to the 1/3. Because it says it right here, y equals x to the 1/3. So the y value of this function is x to the 1/3. The y value of this function is x squared. You know how sometimes we write the ordered pair on this parabola, we write it x squared, right? The x value is x, the y value is x squared. So when I ask you, so keep that in mind today, when I ask you what's the y value right here, what's the y value at this point, you say x to the 1/3, right? What's the y value of this point? X squared. The y value is x squared. Okay, all the y values on the parabola are x squared. Okay, so back to this, John.
So where does this come into play? Like when do you use this? Because obviously with the area under a curve, you figure out position and stuff.
Really good point. You know, I told you we're going to be slicing those lemons next week and doing volumes. Okay, so where this can come into play, one place this can come into play, let's see, is recent. That's not what I want. Hang on here a minute. Okay, one place this can come into I don't have a really great example here of a curve that's bounded by two, yeah, I do too. Here we go right here. Okay, so one of the things, you know those problems we've been skipping that talk about a volume of a solid, right? I said we've been skipping that. Okay, here's how we're going to do this. We're going to find the volume of the solid, the three-dimensional figure, that is created when this region, which is a region between two curves, is revolved around this axis of revolution. We're going to find the volume of of that solid. Now it's kind of hard to see it, okay? But we're gonna find the volume of that solid, and it's created by this region. So being able to set up an integral with that region is one way to do it. Now this is a simpler one. Now this isn't between two curves, but like the volume of this thing right here. That kind of, I mean, that's just one quick example of where that can be used. But we'll see it in some other examples too. I think just like with our velocity acceleration kind of thing, not as much probably, but that's the real important one where we have to be able to do these regions and think of these strips. Notice this is like our strip. That's like our little rectangle right there. So so looking ahead, that's one place where we would do that. Okay, so again, the idea is we're just thinking of using the integral to add up the area of all these strips. The area of the strip is the width, which is dx, and the height of the strip, which is going to be the top y value minus the bottom y value. So for our notes, do you want to write this down? So up on top here, so the first one that I have there, so we're going to do the area between two curves. The way we do it is we simply do the integral of the top curve minus the bottom curve. Now I wrote f of x minus g of x. The last example we had, the g was on top, didn't matter. Now, you can probably imagine some complications might come in. What if you have a function that crosses itself the other function a couple times? What if one function's on top? Think of sine and cosine. If you grab sine and cosine together, sometimes sine is on top, sometimes cosine's on top, depending where the region is. So you may have to split it up into parts. Okay, so that could happen. But so number one there, I say that's with vertical strips, okay? Top curve minus bottom curve. And the reason we do top minus bottom is because we want it to be positive. We want to take the bigger y value minus the smaller y value. And so we want that to be a positive number. That's why we do top minus bottom. And then the dx is the width. Notice I made a little note up here. It says we're always going to get a positive area, right? That's why we're doing it that way. Now, number two down below says sometimes we can do these problems with horizontal strips. Now, you might look at that and think, well, why bother? And it turns out that there's going to be some problems where that's really the only way to do it. There's going to be some problems where really the only way to do it is because of with horizontal strips, because of the nature of it. It'll be much more complicated to do it the other way. But we would prefer to do vertical strips. That's what we're used to. Now, what changes if you're going to do it with horizontal strips? Well, now you're doing right minus left. Again, you want the bigger number minus the smaller number. So the right-hand x-coordinate is going to be bigger than the left-hand x-coordinate. And notice it says f of y minus g of y. In other words, we're going to be subtracting x-coordinates, not y-coordinates. And so the functions are going to have to be switched in terms of y's. Okay, and notice the width there is dy. So let's take a look at how this would have looked on that very same problem. Okay, so remember when I made a point right here? Remember when I wrote this point right here? And I said that every point on there has coordinates x squared, right? That's true. But also, every point on there has a y-coordinate of y and an x-coordinate that is square root of y. Wouldn't that be true? Okay, so think about this point right here. This might be, well, it'd be negative. In this case, it'd be negative because the x is negative over here. So we'd have to say that'd be negative square root of y. But that's not an issue we don't have to really worry about. But it maybe it'd be better to pick a point over here. So you could say, okay, that's going to be a point x squared. Or you can also think of that as being the point square root of y. Okay, now this would be a point, let's say this would be the point 3, 9, right? So you could think of that as 3 and 3 squared, or you could think of that as square root of 9 comma 9. Okay, now another way we can see that, let me do it in red, is we could just solve this for x, and we get plus or minus square root of y. And of course, the negative square root of y is when you're on this side, the negative x is positive square root of y is this one. Same with this equation. We can solve this for x, and we can write this x equals y cubed, right? So every coordinate on this can either be thought of as x comma x to the 1/3, or it can be thought of as y cubed comma, y. Okay? Because it says y equals x to the 1/3. This equation says right here that the y is equal to x to the 1/3. So the y is equal to x to the 1/3. Or if I solve it for x, it says that x equals y cubed. So every point on this graph, the x is the same as y cubed. Right? Okay. So if I ask you, so let's go through this. So if I ask you, what is the y coordinate on this graph? What are you going to tell me? What's a y coordinate on this graph? X squared. What's the x coordinate on this graph? Square root of y. The x coordinate on this graph is square root of y. How come? Because you can solve for x and it'll say x equals square root of y. Okay. Why that's important is because then I'm going to tell you we got to take the right x coordinate minus the left. So in other words, what I'm trying to say to you is another way to find this area would be to add up a whole bunch of rectangles that go this way. Doesn't it make sense that that would give you the area? If you added up an infinite number of skinny little rectangles that went this way, that would also give you the same area as if you added up a bunch of rectangles going that way. Right? So now let's draw in one representative strip in red here. Let's just draw in one right here. Okay? So, what is the area of this strip? Well, the width of the strip would be this wide. Well, now if this is delta x, change in x, what's this? Change in y, right? That's up and down. So the width of a sideways or a horizontal rectangle is going to have a width that would be delta y. That width right there would be delta y. So that's why we get a dy right here. What's the height of this rectangle? Well, the height, it's laying on its end. The height is this x coordinate. Now, what did we say this x coordinate is? What's the x coordinate on this graph? Square root of y, right? That's weird. I asked you for the x coordinate, you give it to me as a y, but that's what it is. Because right here, the x coordinate on the parabola is x equals square root of y. So this x coordinate is square root of y minus this x coordinate. What's this x coordinate? What's this x coordinate? Y cubed. Because on this graph, the x coordinate is y cubed. So this x coordinate is y cubed. So it'll be square root of y minus y cubed from what to what? These strips, we will add up from 0 to 1. Now it turns out to be the same as if we're doing x's, just because this point is 1, 1. Okay, now let's check it on our calculators. Let's go back to the one we did a minute ago. Let's go back to this one. So type that into your calculator. So let's type that into our calculator right there. And that should be that blue, the area between there. That would be adding up these vertical strips here. What do you get? How much? 5/12. Okay? Now let's type in this. And I'd go ahead and type it in with the y's. Actually, type it in with the x's. The calculator's not going to know the difference. Those would be inverses, and the whole region would just be flipped around, but it's the same region. But anyway, I think it's smart. I think it's good to just type it in with y's in the calculator. Okay, I mean, you can type it in with u's or z's or w's, right? That wouldn't make a difference, but you get the same thing. Better get 5/12, right? Okay, so the idea is that when we have a region that's between two curves, we can find that area by adding up a whole bunch of vertical rectangles, infinite, or we can add up a whole bunch of horizontal strips, rectangles, right? Either way, either way. In this problem, it'd be just as easy to do vertical, so probably if we do vertical, we would just do vertical. Okay? All right. So, let's go ahead and do, this is number 1. So if you want to go to your homework, I never handed out a homework sheet, did I? Well, I'll put it up here. Okay, number 1 is going to be a problem on your homework. So if you want to turn to what would maybe be your homework page, we'll do number 1 here together, and then I'll also help you on another one that's going to be a part of your homework. at least help you draw the picture. Okay, so this is number 1 on page 420. It says, let R be the region between the curves y equals x and y equals x squared. Let y be the region. Let R be the region between the curves y equals x squared. So I've drawn it. Now I made the parabola a lot fatter or flatter, I guess fatter and flatter, just to draw that region, because it's kind of hard to draw the y equals x and get a very big region that you can see and work with very much. So part A says draw a sketch of the region. Okay. B says use 5 left rule rectangles to approximate the area of R. And then C says draw a picture that illustrates this. Use the picture to decide whether your answer is an over or under estimate. Okay, so let's go ahead and do that. So let's go ahead. These are gonna again meet at the point 1, 1. Okay, so let's draw. You're not gonna have to do very much of this. You might maybe one more time in the homework have to draw some rectangles. Okay, but otherwise we won't spend a lot of time doing this. So here's one. So if you're gonna do 5 of them, you're gonna have point 2. Not spaced out very well. Okay, so it's going to be about 0.2 wide, so 0.2 is going to be your width. So left rectangle, here at the first one, they're going to be just nothing. Okay, at the next one, it'll look something like that. And the next one, remember, you don't go to the x-axis, you go to the curve. And you draw across. Oops, that should be right on the curve there. And then the last one. Right? So, it looks something like that. And these points wouldn't necessarily hit right on the curve. The right-hand sides. Right? The right-hand sides aren't going to hit exactly right on the curve, probably. Right? I didn't draw that very well. But anyway, okay? So our next quiz, you're not going to have to draw these in. But the idea is we could approximate this area by adding up these rectangles. Okay? So what would we have? We have one y equals just x and one y equals x squared. So we would have our width, which would be 0.2, and then again, our height of our rectangles is just going to be each of those functions subtracted. Now, which one's on top? Which function's on top? Y equals x is on top, right? So that y value minus the other y value. So the first one's going to be 0 minus 0 squared plus, and I just factored the width out. I just took the 0.2 out. And then it's going to be 0.2 minus 0.2 squared. Right, because the next one's going to be 0.2 is going to be on y equals x. But now I could write f of 0.2 and g of 0.2. If I name those f and g, I could do that. But I think these are simple functions, so we don't have to do that. Plus, and this could be 0.4 minus 0.4 squared. Right, because that's what it's going to be. 0.4 minus 0.4 squared. 0.4 squared is 0.16. So that'd be 0.4 minus 0.4 squared. That would be that height right there. Plus 0.6 minus 0.6 squared, and then finally 0.8 minus 0.8 squared, and we would stop short because they're left rectangle, right? And then you can type that into your calculator and get the numerical answer. So that's parts B and C, a little picture of it, and then that. Okay? So if you run into one that says midpoints, you run into one where you have to draw a few rectangles, that's the idea. But again, it's just reinforcing the idea that to find this area, think of these rectangles. So, Okay, so you can add that up and go. So what I would like to do here with this is, now let's go ahead and pretend we had vertical. Let me change colors here. So now let's ignore those rectangles. So I'm gonna, I don't know if I erase it, I still erase it. Okay, so now I'm just gonna think, okay, let's imagine a skinny little rectangle in here. I'm gonna do an infinite number. So this blue strip, I'm gonna call it just a strip now, but when I say strip, I mean skinny little rectangle, right? Skinny little rectangle, so skinny, I'm gonna have an infinite number of them, so skinny that the width is nothing, okay? But, so I'm gonna take this one strip and I'm gonna add up a whole bunch of those strips to get the area. Well, what is the height of that strip? So here's my integral, it's gonna be my adder, right? An integral is an adder, it's sigma notation, right? So what is this? So now we'll see how you do on answer me. What is the y value of this point? The y value of this point is x. Very good. Why? Because on that curve it says right there that the y is equal to x. So what's the y value? It's x. Minus, what's this y value? X squared. This y value right here is x squared. Why? Because it says right there that y is equal to x squared. So the y is x squared on this one. So I'm going to take x minus x squared, just like we did up here, right? We took x minus x squared, x minus x squared, x minus x squared, right? And then times the width, which is dx, and the strips are going to fill this space from 0 to 1. We're going to fill that space from 0 to 1. Now, if this would have been the point 24, we would have, if this would have been the point 24 right there, the strips would have filled the space from 0 to what? 0 to 2. They would have filled the space from 0 to 2 because we're going left to right, so from 0 to 2. But it's 0 to 1. Now, type that in your calculator, see what you get. How much? 1/6. Now, that finishes question 1. But just to reinforce the idea, and you don't have, I mean, you can write this down or not as part of that. Let me take that same region and say, but you know what? I could have added up a whole bunch of horizontal strips. Right? Well, what would that integral have been? It would have been this x-coordinate. What is this x-coordinate right here? And again, we want to do right minus left. We want to take the bigger x minus the littler x. What's this x-coordinate right here? We would want to, right, we want to solve that for x. This x-coordinate right here is square root of y. Minus this x-coordinate. What's this x-coordinate? It says right here that x is equal to y. So minus y. And then the width dy. We don't need parentheses around that. But that would be this x-coordinate minus this x-coordinate. The bigger x-coordinate minus the smaller x-coordinate. And then that would fill the space. This is a 0.11. So these strips fill the space from 0 to what? What if this point would have been 2, 4? These strips would have filled the space from 0 to 0 to what? Up to 4. 0 to 4. See how we would use the y in that case, right? Here we got vertical strips filling the space from an x of 0 all the way to an x of 1. If it was this point, it would have been an x of 2. When we're doing horizontal strips, they're filling the space from 0 up to whatever the y value is. So it would have been 0 to 4. And it makes sense that if you're doing an integral in terms of dy, that these numbers would be y numbers. Remember when we did u substitution? We talked about these are x numbers, and then if you do u substitution, they become u numbers, and they change. So if you're doing a dy integral, if you're doing horizontal strips, you got to do it in terms of y's. These numbers are y values. Okay, very important. Now, anybody type that in? We trust it? It's 1/6. Okay, it's going to be the same answer. Okay, now you didn't have to do that in number 1 on the homework. You didn't have to do that, but, okay. All right, so finally, this one right here. This is number, I think it's either number 3 or 4 on your homework. Let me pull that up here real quick. Number 3. So this is going to be number 3 in your homework. Okay? So I'll give you a minute to draw this picture. This is going to be number 3 in your homework. Okay? So it says, and it's also an example in the book. You might want to draw a fairly good sized picture of this. Okay? It's also one of the examples in your book. Now, so one of the things we'll have to get good at here is understanding the region that they're describing. So what they would have said on this one, well, let me just read it while you're drawing that. Well, it actually doesn't give a description. So let me just take a stab at it. This problem would say, find the area of the region bounded below by y equals -1, bounded above by y equals 1, bounded on the left by x equals 1 minus y squared, which is a sideways parabola. So we're going to have to kind of be able to sketch these things, which a lot of times we're going to use our calculator anyway, so we can do it with our calculator. And on your calculator, instead of going to function mode, you can go to relation mode. If you get an x equals 1 minus y squared, if you get one in terms of like that, you can go to relation mode to graph them. It's nice. Bounded on the left by x equals 1 minus y squared, and bounded on the right by x equals y plus 2. Okay? Now you could subtract the 2 and make that y equals x minus 2 to figure out how to graph it, whatever. But that's how they'll tell you the region. So you'll have to draw those graphs and figure out that region. Okay? Now, the one that they gave you, the one that they did for you in the book, and this is the point 1, -1, and this is the point 3, 1 right here. That's 0, -1. Okay, so these are all of these points right here. Okay, now, in the example in the book, they did this with horizontal rectangles, horizontal strips. So let's talk about this. I've given you 2 examples so far today where we could do horizontal, vertical strips. They're about the same, and it's like, what's the big deal? Well, here's the big deal. Because if we were going to try to do this with vertical strips, if I draw a strip in here that is right here, the top curve is going to be this one, and the bottom curve is going to be the parabola. But if I draw a strip over here, the top curve is still this, but the bottom curve is something else. And if I draw a strip right here, you see how those are all different? And so, and this is what you're going to do in problem number 3. In problem number 3, now it's a lot of wording, but it's going, in problem number 3, they're going to say, find the area of the region bounded below by the x-axis, above by the line y equals 1, on the right by x equals 1, and on the left by the curve x equals 1 minus y squared. Well, here's the line x equals 1 right here. Okay, so let me read that again. It says, find the area of the region, so this is 3a. Find the area of the region bounded below by the x-axis, above by the line y equals 1, on the right by the line x equals 1, which is here, and on the left by the x equals 1 minus y squared. In other words, they're saying find this region. Part B is going to have you find this region down here. And then part C is going to have you find this region, which is actually just a triangle. But so if you were going to do vertical strips, you would have to split this into 1, 2, 3 different regions. Why? Because if you go outside of any of those regions, the top and bottom curves change. So here, all through this region, the top curve is this line, the bottom curve is the parabola, so you're good. But once you get into here, now that changes. Okay? So I'm going to leave that to you to finish that part. Okay? What I want to do is show you what they did is why horizontal strips are much better on this problem. Because look at this horizontal strip that I draw right here. Okay, now you don't have to do this in your homework, but I just want you to see this. wouldn't every red strip I draw, every single red strip in here, wouldn't it touch this line on the right? And it would touch the parabola on the left, wouldn't it? And so you could do this whole thing with just one integral. If you do vertical strips, you'd have to divide this up into 3 different pieces. So horizontal strips can be an advantage. Okay, so let's do it. I'm going to do the red one here. You don't have to write it down because on your homework you're doing the blue. You're doing those 3 different regions. But what would be our horizontal strips? It would be the right. So what is this x coordinate right here? Remember, whenever you're doing horizontal, you're doing this x minus this x. Because that looks like about 2.5, and that's about 0.8. You'd want to do 2.5 minus 0.8, right? You want to subtract the x's. Now, we're not going to do that. We're going to do the equations. But what is this x coordinate right here? Right there. Y plus 2. So we're going to do y plus 2 minus, and what's this x coordinate? It's the parabola. It's 1 minus y squared. Now we got to put that in parentheses. Now you could simplify that if you want, but you know what? You might screw it up with that negative sign. You better put parentheses around. I just type it in like that. But you could simplify it first if you want. The width is dy. So this x coordinate of this line is right here. Y plus 2. This x coordinate is right here. 1 minus y squared. So when you guys do the blue, you're going to have to solve these for y. Now remember, when you do the square root, you have plus or minus. Plus would be the top half, minus would be the bottom half, right? So which one you're using? Up here you'd be using the top half. Down here you'd be using the bottom half. So you have to use the negative square root. Okay? So we'll check over that tomorrow, but that's what you got for your homework. Now the red strips are going to fill the space from where to where? We always want to go from little number to big number. -1 to 1. Now, they already did that in your work here. -1 to 1, and I think they got 8/3. 8/3 is what they got for an answer. Okay? That's 8/3. Now, if you do the blue pieces in your homework on number 3, they should add up to 8/3 as well. Okay, so that just shows how that's a great example of problem where horizontal strips would be a lot better to use. Okay, all right. Oops, I'm getting into the other class. Okay, so 7.1 homework. This line right here. We already did number 1. Okay. Now, once you get to 10 on, well, maybe not 10. 10, you got to answer some question about distance and stuff. So that's you don't have to draw anything or calculate anything. But yeah, 17, 23. So what they do is, so you're going to have 17 and 23. It says sketch it with X's or solve them with X's. So that's going to be vertical strips. Okay, so 17 and 23, you're going to do vertical strips. And then on 29 and 35, you're going to take those same pictures, the same picture, and do horizontal strips. So 17, you'll do the same picture you'll use for 29. Okay, so a lot like we've been doing today, where we did it with vertical and with horizontal. That's kind of what you're doing on those last ones. All right. Save that number 2 on 2014. We'll do that tomorrow. Okay, sorry, I want to give you some. Yes. Yeah.
Did you hear this meeting?
Which one?
Did you guys?
I haven't heard yet. They're talking about it. Did they say anything for you guys?
No, I just started tweeted something last night.
The tennis. That was tennis.
Was it? Oh.
Yeah, I was confused too because it said North Platte and they had a little emoji that was a tennis emoji. And so, because they always do have a tennis meet when we're there for the track meet, and so that was their tennis. But they're talking about it because it's supposed to snow there on Thursday. Now you get Columbus, I don't think. It's gonna be cold.
Cold, but it's not supposed
It's gonna be cold, not snow. Yeah. Wednesdays would be nicer if they would move yours to Wednesday. It'd be nicer, but they probably won't just for the cold one. Yeah, I know.
Oh, that's how I came back yours fully charged and this one's like yellow. Oh, and I can use it. That's fine. Ow. Oh. Ow.
And now now it looks like they've taken some of the moisture out of the forecast. So possibly we'll wait till Thursday.
Operation and activation. Two.
It feels messed up. Already messed up.